My name is Renellyz Perez, and I'll be talking about a pilot study that I'm leading to observe upper ocean currents and vertical shear in the tropical Atlantic. This program is called the Tropical Atlantic Current Observation Study, or TACOS. The Prediction and Research Moored Array in the Tropical Atlantic, or PIRATA program, has been collecting moored and shipboard measurements across the tropical Atlantic for over 23 years. PIRATA is a partnership between France, Brazil, and the US. PIRATA moorings make standard atmospheric and oceanic measurements like temperature and salinity. Some of the moorings are augmented with one near-surface current meter. PIRATA started to understand how the coupled ocean-atmosphere system affects the variability of sea surface temperatures, wind, and rainfall in the region. We do this because SST, winds, rainfall, impact climate and society. Amazon droughts and record hurricane seasons can happen when temperatures in the tropical North Atlantic are high relative to the tropical South Atlantic, and flooding can occur when temperatures are low. On a shorter timescale, we want to provide ocean observations for improving marine weather forecasts, including hurricane forecasts. PIRATA mooring data is available in real time and are used by operational models. We don't have many measurements of near-surface velocity, much less vertical shear in the near equatorial Atlantic. Here it is important to measure velocity and shear because they impact distributions of temperature, salinity, and nutrients through horizontal advection, mixing, and air-sea exchange. Of interest to me is how velocity and shear are modified by density changes, wind changes, tropical instability waves, near inertial waves, and tides. If models represent any of these processes poorly, they will have biases. We need time series data to assess model biases. Enter TACOS. For the past 3 years, we have augmented the 4 North, 23 West PIRATA mooring at the boundary between the eastward flowing North Equatorial Countercurrent, or NECC, and the northern branch of the westward flowing South Equatorial Current, or SECN, with up to 10 additional current meters. The idea behind TACOS is that we could move these instruments to different PIRATA moorings to look at the structure of velocity and shear in different key locations. For example, the oxygen minimum zone region or the main hurricane development region. In real time, once a day, we receive hourly data from the mooring. In the first and third deployment, we had 11 sensors out there, but in the second deployment, we only had 5 sensors that were kindly loaned to us by PMEL. The yellow circles show the depths that were sampled in the second year. From surface meridional velocity observations previously collected in the region, we also expect to see weak mean poleward flow at this location, on the order of 5 to 10 centimeters per second. In the bottom 2 panels, you see the full time series of zonal and meridional velocity, which has been 5-day low-pass filtered, but there is high variability on those short time scales. We vertically interpolated across data gaps for this image. The first thing that jumps out at you is the high-frequency fluctuations, predominantly in meridional velocity. These fluctuations are associated with tropical instability waves propagating westward across the mooring. The black line is tracking the depth of maximum shear squared, and the gray line is tracking the depth of the base of the mixed layer. What you see is that the maximum vertical shear squared is often found at or about 10 meters below the base of the mixed layer. As we expected, the mooring is located in the southern edge of the eastward North Equatorial Countercurrent, and the black line shows ordered 10 centimeters per second 3-year mean eastward flow. This flow is strongest near 37 meters rather than at the surface. The wind-driven northward flow on the right at the surface is a lot weaker than we expected. There is significant variability in the record means, especially for zonal velocity. During TACOS 3, the blue line, we see much stronger eastward flow than during TACOS 1, the red line. Regardless of the year-to-year variations, in all 3 deployments, maximum vertical shear is found near 30 meters depth, just above the mean base of the mixed layer. Unlike at the equator, where you have a strong equatorial undercurrent, both components of velocity have strong vertical gradients. You can see that with only half the sensors, the shear is underestimated during the second deployment, the green line, which is far weaker than the shear observed during the first and third deployments, the red and blue lines. Back to time variability, we found that zonal velocity exhibits largest interannual variability. Based on analysis of drifter altimetry surface velocity data, the year-to-year zonal velocity variability is mostly geostrophic, and it is influenced by the large-scale circulation. So for example, by the position of the SECN-NECC boundary, and by the strength and position of the North Equatorial Countercurrent core. And more recently, it's impacted by the Atlantic coupled modes, the meridional mode and the zonal mode. From 3 years of data, we can begin to form a seasonal cycle. Seasonal amplitudes are weak at all depths, less than 10 centimeters per second, and they are comparable for both zonal and meridional velocity. The time series is not long enough to define a significant seasonal cycle, but we can see that the strongest northward flow at the surface is in late spring and winter, and the strongest subsurface southward flow is during the summer when tropical instability waves are prevalent. A lot of the observed velocity variability is high frequency, and this can be seen from spectra of meridional velocity at multiple depths. The mean currents are weak compared to tropical instability waves and near-inertial internal waves with 4 to 9 day periods. Meridional velocity high-frequency variability greatly exceeds that of zonal velocity. This is clearly illustrated from zonal velocity spectra, which has significantly less energy. Both components of velocity exhibit a strong semidiurnal cycle, especially zonal velocity. Diurnal and semidiurnal variations are being explored further by Jonathan Christofferson and members of our group. Very energetic summertime tropical instability waves were observed in 2017 and 2019. These are the westward propagating features that you see in SST. This was quite surprising because the equatorial Atlantic was anomalously warm, with Atlantic Niño-like positive temperature anomalies, which traditionally imply that tropical instability waves will be weak. The unexpectedly strong tropical instability waves are due to stronger than usual SECN NECC shear, which provides energy for the tropical instability waves. We observed at least 9 summertime tropical instability waves during the record. The start of each TIW is shown by the black vertical lines, which are associated with the maximum northward flow at the surface. Up to 1 meter per second meridional velocity fluctuations were observed in 2019, which is impressive given that the mean flow is less than 5 to 10 centimeters per second. Periods were between 24 and 33 days for the TIWs, and the most commonly observed period was around 29 days. These TIWs may be important for property advection and vertical mixing and entrainment in the tropical Atlantic, so that's why we study them. They are also nonlinear and rectify back on the mean flow and the winds. From the 2017 TIWs, we formed a composite, and we learned that the TIW velocity structure is not symmetric in time, although zonal velocity is more symmetric than meridional velocity. In the middle panel, you see that the northward flow forms in the first 2 days, and then southward flow propagates upwards from days 4 to 10. This alternates then to northward flow again, moving upward at the end of the wave. This upward propagation of signals has speeds of about 12 to 15 meters per day. We observe the largest temperature signals at around 70 to 120 meters depth. We saw subsurface cooling when the thermocline shoals and warming when the thermocline deepens. We haven't had a chance yet, but we plan to examine the composite TIW structure for the 2017 through 2019 TIWs. What we can say is that these eddies contribute to the sea surface temperature budget. This is clear from the SST tendency term on timescales of 20 days and greater, which is the gray line, which shows strong covariability with the meridional eddy advection term, the blue line. Here we focus specifically on the 20 to 50 day bandpass variability to estimate the eddy advection terms. Meridional eddy advection exhibited the largest variations during the summer 2017 and 2019 TIWs. In a 2020 paper, Gregory Foltz looked at the contribution of high-frequency motions at 4 North 23 West to the mixed layer heat budget. Using PIRATA mooring and TIWS data and a KPP model, he found that the elevated shear during TIWs can generate significant monthly mean turbulent cooling on the order of 15 to 30 watts per meter squared. When we do mixed layer heat budgets, we usually have a large residual term at 4 North 23 West, and this mixing can account for a large part of the residual term. This mixing is hard to observe, but it is needed to close mixed layer heat budgets and predict SST. Interestingly, we observe a lot of near inertial waves, sometimes coincident with TIW variations. In the same study, Greg found that strong NIWs were associated with a thinner mixed layer, stronger shear, and stronger mixing on average, compared to periods without NIW activity. However, there was not a significant difference in the turbulent cooling between high and low NIW energy periods. Greg Foltz also looked at the impact of diurnal variations on turbulent cooling. Although we found that the largest shear variance, diffusivity, and turbulent cooling at the base of the mixed layer occurs at night and in the early morning, when the mixed layer is thickest, no rectification onto the mean turbulent cooling was found. We are looking more into the diurnal variability of stratification and shear in a study being led by Jonathan Christofferson. For my last results slide, I will just say a few quick words about vertical resolution. We have learned that you need to observe velocities at small scales, less than 10 meters, to not underestimate vertical shear, both the mean and the time-varying shear. The black line shows a time series of the maximum vertical shear squared that we observed from all of the available sensors. The red line shows what would happen if we had ignored the higher resolution during TACOS 1 and TACOS 3 and pretended that we only had the TACOS 2 configuration. In that case, we would have severely underestimated the vertical shear. This is important because this elevated shear drives mixing. Coupled model SST biases in the eastern tropical Atlantic are due in part to weak mixed layer cooling and entrainment in the ocean. We need more model observational studies to reconcile these differences to see if models are not getting the shear and mixing right at the base of the mixed layer. I just wanted to take a moment to acknowledge all the people who helped us deploy and recover our sensors, process and analyze the data, and funded our work. Thank you. Here are 2 publications if you want more information about TACOS. There are 2 new publications that are in preparation on the 3-year analysis and the diurnal cycle analysis that myself and Jonathan Christofferson are leading. Thank you very much for your attention. In case I'm unable to answer your questions directly after my talk, you're welcome to email your questions to me and Greg. Our plan, in case you're interested, is to next deploy these sensors at the 20 North, 38 West PIRATA mooring, which is in the main hurricane development region. Thank you again.